Alright, so I'm Seth Chiasson. I'm going to tell you guys about heat exchangers for the third time today. So just to go over the different kinds, as Danielle mentioned earlier, you have shell and tube as well as plate heat exchangers, and as was mentioned earlier, CPU coolers. This one has the fan that you wanted earlier. But my presentation my presentation is primarily going to be on this exchanger, which is a fin fan heat exchanger, which is kind of like a supersized version of this one. It uses usually liquid water to carry away heat, but it uses gigantic fans to increase the convection transfer happening across the array. So these are common features of all heat exchangers. Danielle touched on this earlier. There's always a process fluid, a working fluid. In general, the main thing that you're going after is surface area. Heat flux is generally watts per meter squared, so for every meter squared you get, you're going to increase the amount of heat that you can eject out of the system. So for the heat conduction equation, you have your conductive coefficient, which is K, as well as your convection equation, which is just H. So with the fin fan heat exchanger, as you increase the amount of air that you're pushing through it, the more turbulent, the faster it is, you're going to increase your heat transfer coefficient, H, which is overall going to increase the amount of heat you can get out of the system. And that's primarily what we're going to be going over today with the project that I actually did last summer. So for context, last summer I did an internship at BASF in Geismar, really large facility, and I had to deal with this one fin fan heat exchanger where it was record heat during the summer, and as we saw earlier, the heat transfer equation, your delta T is a large driver with how much heat you can get out of the system, so trying to cool off something with hot air generally doesn't work that well. And so my job was basically to figure out how to cool off things with hot air. So I'll be able to walk you through the process. And to show you some of the main components that you see inside of these exchangers is that you have a motor and a fan. The motor will drive the fan and push air through these, similar to the shell and tube exchangers. You have these tubes that carry your process fluid, as well as they have this fin array on there that increases the surface area. And you'll see in a little bit, I actually went through the original spec sheet of this one that was installed on the site, and you'll be able to see how much of a difference those little fins make for the surface area. And so, dealing with those components, you have three main ways to increase your heat transfer coefficient when it comes to convection. So you're going to have the main component is the amount of CFMs that you're able to push through, so the max flow rate of air essentially they're able to put through, and that's directly correlated with the RPM of the fans, so that's how fast that's spinning. Every revolution is another batch of air, so to speak, getting pushed through, as well as the pitch of the blades. As you increase the pitch of these fan blades, you're going to increase the amount of air that you're pushing through per revolution, as well as increasing the static pressure, which basically correlates to how well air can get through a dense fin array and push through it. So to do those two methods, we have two options. You can either shorten the motor fan belt, which would increase the RPMs of the fan. However, that would increase the wear rate of the rubber belt, which is very prone to completely failing. And in this case, in this process, that would be a catastrophic failure. Not good at all, lots of money, lots of time. And so the only option we had was to increase the pitch of those fan blades. And so I had to figure out if we can do that, and if so, to what extent and how. And so this is actually some of the work that I did, some of my handwritten work with some of the specifications. So I had to go find the installation book from the 1960s. The pages were yellow, the ink was faded, and it was literally crumbling in my hands. So that was kind of painful to read. And so some of these are like the manufacturer specs that came out of it. So might be hard to tell, but I have bare tube surface area right there written. It was 1,027 square feet. With all the fins installed, it actually went to 16,000 square feet. So it's a really huge difference in the surface area because of those fins. So using some basic equations that we've seen a couple times today, I was actually able to confirm with the data given that the original heat transfer was supposed to be about 2 million BTUs per hour, and as well as I had to do a lot of work to figure out what was the original pitch installed, which was 10.2 degrees, and I did find out that you could change it to variable angles between 10 and 15 degrees, I believe. And so I was able to figure out how to calculate the different CFMs that you would get at different pitch angles with this equation specifically right here, and convert that into a mass flow rate, and then figure out the amount of heat that you get out of it. And so after doing all that, I was able to make the right recommendations. So we went from about 2.9 degrees to 12 degrees. You didn't need much, but Actually, I did skip over a really important point. So as you increase the pitch of the fan blades, the motor actually has to work harder to push that air. And so I had to make sure and verify that we were not going to burn out the motors the second that we did that. And we did find out that there was enough headroom inside of those motors so that way that wouldn't happen. So after doing that, we were able to get it fixed, we got it changed up, and it did achieve the correct heat duty required to cool off that process. And in case you're curious, the chemical made was NMP, which is N-methylpyrrolidone. It's a solvent, and it's a really high purity because the customer that it was for was actually Intel making the computer chips. And so it's used for like electrical components and cleaning. So that's why this was so important to get this done. And it all worked out really well. And some of the things I learned is that communication is crucial and you have to be able to back up your claims. So when I first went to them saying we can change the pitch angle, all the chemical engineers immediately told me you're gonna break our stuff, and I had to make the promise to them, no I won't, I promise. So it was a really fun project, and I learned a lot of things about heat transfer because this was before I even took, or as I'm currently in heat transfer, so I was able to learn a lot about the process and what goes into it and what to look at. So that's everything for me, if you guys have any questions. Yeah, so
how long did the project take you from like start to end?
The whole summer.
The whole summer?
Yeah. Because I had to ask a lot of questions because I had no idea about what heat transfer really was. I like had a core principle, as well as people have really busy schedules in a plant, so being able to set up meetings with everybody and, like I said, like make that promise, like I'm not going to break your stuff. That took a lot of meetings and showing them all the stuff that I did to show that I actually knew what I was talking about at that time. So it takes a while, but most of the time it's just waiting to get an answer or get a response, honestly.
Gotcha. Did you learn more from like the communication with the other engineers, or did you have to do a lot of learning like on your own?
No, yeah, definitely talking to other people. So it was actually funny because most of the people in the group that I worked with were chemical engineers. There's like 6 lead chemical engineers and only 1 mechanical guy who was pretty much just my they call it my babysitter, just to, if anything, if I messed up anything, it was actually his fault by technicality. But yeah, it was super cool just learning how to like operate in that environment. Cool. So, yeah. Any other questions?
Yeah, just my question. Did they actually redesign the blade because you suggested they increase in pitch, right?
Yes.
So they actually get a new blade design?
No, so they use the original blades. The best way I can describe it is that they had a cutout and you would change the position of the bolts holding in the fan blade. So like you would have 1 bolt here and then 1 there, but there's another hole cut out to re-bolt it higher up.
Adjustable.
Yeah, so between like 10 to 15 degrees, you were able to adjust it.
Okay.
It's just, you know, it was installed in the 60s before most of these people came to even work there. And so they had never heard of changing the blade, so they just assumed that it was fixed. When I first made the recommendation, they thought I was trying to tell them to like cut the blades off with a blowtorch and just like weld them back on at maybe the degrees. So that was part of me having to show them like, this is the original book. I know you guys have never seen it before, but I promise it's real. So, yeah.
Sweet.
Okay, so a couple of things before we